Good afternoon, everybody. Just before we start, what I'll do is just give you a little bit about my background. So my name's Joss Langford. I'm the Chief Technical Officer of Activinsights, and I'm here with my colleague, Raggy Baines, our Commercial Director who met at the door, who gave you some information. So the deal I have with Raggy, my Commercial Director, is that he gets you to give information about our products, do the sales stuff, so I don't have to. So I'm not going to be referring to our products or doing any of that kind of stuff in this talk. What I've tried to do is put some information together to talk to you about the sorts of data that we can collect, that can now be collected with wrist-worn accelerometry, and try and put that in context of the sleep environment. I'm not a trained medic. I don't have a medical background. I'm an engineer by training. But I've spent the last 15 years working with objective data measurement techniques, trying to understand what people do all day, essentially. And obviously, for a large portion of that time, that's sleep as well. So my expertise is more around understanding sleep in the context of everyday living. And the devices that Activinsights produce are devices which are designed for remote data collection over prolonged periods of time. So up to a month with one of our devices and up to a year without any charging or clinician input on our other devices. So that's a little bit about me. Let me tell you a little bit about Activinsights as well. So we're a digital healthcare company. We specialize in the objective measurement of physical behaviors and lifestyles using our wearables and other connected devices. For over 10 years now, health professionals have trusted us to deliver health measures and insights to help them to develop new treatments and innovative solutions. That might be right from therapies through to behaviour change. And we do a lot of work in public health as well. So there's a business that came from public health epidemiology, so specialising in getting large numbers of devices out across large numbers of people for a long period of time. We have over 700 peer-reviewed publications that support our devices and our analysis techniques, and over 100 of those are in the area of sleep. And what we're trying to do always is to simplify the process for you as researchers or clinicians of collecting data in a free living environment. So I'm going to look about some of the recent highlights in the advancement of the use of wearables, accelerometry in sleep analysis, both in the scientific literature and in terms of clinical trials. In the pack that you've got that was handed to you, there is a reference list in there. So up on the screen, I've tried to reference all the little bits of information I've pulled out. There is a list in there. If you don't have it or you would like it electronically, come to our booth, we can scan your badge and we can email that to you, and then you've got that in a more consumable form if you want it. So I'm going to talk a little bit about data analysis, about verification of measures, about validation of measures. And I'm also going to talk about some of the work that we're doing this year in contributing to a global program about thinking about digital health measures, particularly from wearables. What I wanted to do first is to talk a little bit about the difference between actigraphy and accelerometry. So this is a slide, an illustration that came from the playbook, a digital clinical measures playbook, which is something we contributed to last year with the Digital Medicine Society in the US. So this is an illustration out of that pack, and I will talk a little bit more about that work that we're doing with them later on. So this is a pretty typical system. On the left-hand side there, we've got a wrist-worn wearable. That's going to put some data into some software, which will then contribute some data within a wider system, into a clinical system or to a research system or an EDC. Within the wearable, then there are sensors that interact with the environment and interact with the participant. It's a pretty generic kind of picture. So in a traditional actigraphy product, there are algorithms that sit on board that device. And those algorithms are normally proprietary. And they pre-process the data. And that's historically because if you go back 20 years, we didn't have the battery power, the memory power, or the capability to be able to restore all the data from the sensors. We had to make decisions about compressing that data into epochs on the device, a very pragmatic route forward that has allowed many, many good studies. What we were able to change, and this is the GenieActive product was one of the first ones to do this, going back now about 15 years, was actually as we had more data storage available. So our first devices had data chips from an iPod, from the first iPod, so we had exactly the same memory chip on there. So it's only because those consumer devices became available that our technologies have been possible. We were able, rather than applying algorithms on the device, we're able to write all the data down and essentially produce what looked like a pretty dumb device. but clever in what it enabled us to do scientifically. So when we talk about accelerometry, we're talking about the ability to take acceleration measurements and record them all at the sensor level. And importantly, to be able to do that in SI units and to do that in an open format. Because now we can think about reproducibility across different studies. We can think about longitudinal studies as well. Because one of the things that we've seen over the last 15 years is the base technologies that we use, the measurements we take have stayed the same. What's evolved dramatically is the algorithms that we can use to apply to that data. And by recording raw data, we can future-proof those data sets. So the data that was collected 10 years ago with our devices is still just as valuable as recent data, and you can use more recent algorithms to do that. So that's the paradigms that we're talking about here. What does that mean then in terms of data? So here's a representation of a typical counts-based activity plot that will be very familiar to you, a section out of a double sleep plot. Incidentally, the lines here have been put in as an estimated Ben and Rice time based on automatic algorithms, and I'll talk a little bit about that later on. So that's an actigraphy view. If I look at the same data, so that's a view using raw data accelerometry. The bottom, the yellow doesn't come out brilliantly here, and hopefully my next slides show a little bit more detail. The bottom section there has got temperature and light that you'd expect anywhere. But on the top line, what we've done is we've taken the accelerometer signal and turned it into a posture signal. So one of the things that's interesting about an accelerometer is that when it's moving, or connected to someone who's moving, it's a very, very good proxy for activity. But when it's not moving, it measures acceleration, and there is 1 g of acceleration keeping us on the ground all the time. So it turns into a very, very sensitive posture sensor. And that's very interesting in terms of sleep. So that top plot, up on that plot is arm up, down is arm down, and the color changes that you can see are the wrist rotation. So this is the sorts of information that you can see, what we call at the low frequency end from this device. And so what you can see here very clearly is a change from activity during the day to activity during the night. But I'm not measuring activity, I'm measuring posture. So I can see the different postures, I can identify those different postures, I can look at the posture changes. And I can also then characterize breaks in that sleeping period on their activity classification as well. So I can tell the difference between ambulatory WASO as opposed to non-ambulatory WASO because I can understand posture from it. So that's just one snapshot, and I'll show you a little bit more of those as we go through. Actigraphy counts then historically typically stored with a small range of algorithms and a list there, and there are others as well, and you will, I'm sure, all be reasonably aware of those. Almost all of those are variants of, and I excuse the technical language, of a simple what we call a low-pass filter. And essentially that says that all the fast-changing stuff it gets rid of, and it's looking historically. So all the algorithms that you're used to seeing in the world of actigraphy look retrospectively, they say from this point onwards, based on what's happened previously, how can I predict wake or sleep? And that's the way that they've had to work because of the environment they've come from. And what the early work did in accelerometry was to show, although we've got a different technique, which has got much more potential, we've got to show equivalence to those early systems. And so that's what that did. So this is just a quote from the paper back in 2013, just gives you an idea, and I certainly know that use is around at the conference here as well, that when you look at that data on an epoch by epoch paper, you get very, very good agreement between that, which is what you would expect anyway, because they've got the same sensors, but publishing that's really important. One of the other things that it picks up is that when you start looking at the raw data in SI units, you get better equivalence between devices. And that was an interesting finding out of this. So your inter-device correlations are better. So you've got the potential to be able to produce more reliable measures as well. And then what happened lately, and this is some information from a more recent paper from last year, is to demonstrate the equivalence on some of these key digital measures of sleep that you would have expected from actigraphy. So you start off by looking at, does it do the same thing on an epoch by epoch basis? Can I get the same measures that I would expect to get from it? And so there's a list there, and there shouldn't be any surprises there, but it's great to have that demonstrated in the literature so solidly. So the next thing then is to say, right, fine, I've got to a level place now. I can show that accelerometry is at least as good as actigraphy. What else can it do? Any questions at this point about actigraphy or anything else? Yeah, please.
In relation to the accelerometry, does it matter where you wear it on your body?
It does matter. There's a sort of rule that we would use as a measurement scientist that I'd want to put the measurement devices close to the thing I'm interested in. And that's, when you look at that in different areas, that's sort of, you get some interesting questions. So for example, people looking at gait might want to put it on the ankle. The problem is, or the challenge is, about how much patient adherence you get to the wear protocol that you decide. So it does matter, you want it as close as possible, but you also want them to wear it. And what we see again and again is that wrist-worn placement gives us the best patient adherence, and it gives us pretty good data. It can be quite cluttery data, and sometimes people talk about it as noise. It's not, it's just signal we're not naturally interested in. We're a social species with a lot of culture, and a lot of that is expressed through our hands. So you end up measuring that. And what we're beginning to learn, and you'll see more and more papers about that, is that we can use that signal to be able to predict behaviors better. So the wrist is a good place for a couple of reasons. In certain applications, it may be better to put it in other places. And so upper arm is a familiar placement, waist, a lower back for some gait things, ankle if you really, really have to, but it's not liked by participants. I'll move on a step then. So posture detection, and I talked about this a little while ago, and I'll just give a little bit more detail and some more illustrations on this. So there are two papers that are listed that are in the pack that you can get there that will talk about waking posture position particularly. And one of those is called the sedentary sphere, which is sort of 2014, and there's some improvements on that with an algorithm called SEDUP. And essentially that recognizes that when we're looking at sedentary behaviors, we can classify sedentary in two ways. We can talk about that from a metabolic equivalent perspective and say that it's below 1.5 METs if that's the world that you live in, or we can say it from a posture basis that a sedentary behavior is one which is lying or sitting. Now, the difference between lying and sitting is quite difficult with the wrist. And you will see in many studies thigh-worn devices used, which can be very good for that. But again, they are difficult to deploy at scale. And so a lot of the study work that I do is to understand how we can best predict thigh posture from the wrist posture. And it's quite interesting about how you can do that. So this is 24 hours worth of data, and it's the same plot as before, where up is arm up and down is arm down, and the color is the color change. So we can see a clear change of behaviors here where we've not got any positions where the arm is down. And when the arm's down, that's always very distinctive of walking behaviors. Yeah, because your arm is down, the action is down, so ambulatory is very, very easy to detect through that. And we've moved through here, and we get to this point here. We've got a rise time here. We've got ambulatory behaviors in the morning. And then we've got this very interesting behavior here, where you can see that the arm has not been able to descend below the vertical. And you see this in everybody's data that goes to school or works in an office, because when you're sat in front of a desk, you can't move your arm down past the vertical. So you can use this information to infer very accurately some of the different behaviors. And you can see during the night time here, we've got different postures that we're able to show. Now, what we're seeing there is the posture of the arm. And we know in active behaviors how to relate that to active behaviors. And the research is beginning to grow in this space now about how we can translate that into sleep postures. So because it's not an academic talk, I can use lots of references. And this is one from LinkedIn, believe it or not. But this is a guy who's, it's some data from his master's thesis. And I just saw it. It's really, really nice what they've done. So I talked about the color change on that plot earlier, representing wrist rotation. Well, this is exactly the same. So we've got one subject on the right side there where they've taken all the different sleep postures. So they've taken the sleeping periods and they've identified the different sleeping postures and they've related that to the rotation of the wrist. And what's very distinctive is that within the rest of this work, and then they've scaled that up to and you can see distinct clusters of wrist positions, and they've shown how that correlates to different sleeping postures. So you find lying on your side or whatever those postures are. So I can't find peer-reviewed publications in this area, but we will do pretty soon, I'm pretty sure, because I'll do it if no one else has. So you can see, so you can imagine that if you're looking straight down there, that's the position of the wrist, and you can see that they preferentially have the wrist in a couple of different positions depending on that posture. And if you think about that from a biomechanics perspective, that's quite logical. So micro movements, that's another thing that we can do with an accelerometer, which you struggle when you reduce that to actigraphy. So we do a lot of work in Parkinson's. where we were able to detect tremor, frequencies and intensities. We were able to do that during the night. And I'm going to show you a little bit of data around that as well, where we're also looking at bradykinesia. Nocturnal scratch is another area where we do a lot of work, so we can use the device to be able to detect scratch. So those very small micro patterns, characterize those and look at those. It's interesting that doing that during the day is very difficult because scratch is quite confusing. That action, there are many other actions that might be like that during the day, but at night we get much, much better specificity. So both those areas are medical are measures that are being investigated and pushed towards FDA approval. And I don't know so much about these areas, but in terms of restless leg syndrome, there's a paper that I missed off, which is a very good one that was out just last year, and also periodic limb movement disorder. And again, going back to that question about placement, there are situations there where the risk may not be appropriate to look at that. This is just another look at how you can think about accelerometry data. And so rather than looking at it from the static, so looking at that posture stuff, we can actually look at the frequency domain. So we can analyze the signal and see what frequencies are present within the signal. And this is data from a Parkinson's patient. You've got a time scale across the bottom there in local time, so you can see that that's a pretty disturbed night of sleep. On the top, it gives you the sort of the total movement intensity. So those high lines up there would say that they are active and clearly non-sleep. And then you can see those interspersed at the bottom. The bottom section of the plot is a frequency domain, if you can't read it, so that's 0. So these are the sort of static postures. And then 2 hertz would be a movement that's twice a second. And then 4 hertz would be a 4 hertz second, and then you're getting up towards 8 hertz and 6 hertz. So one of the things that you can see here when we see this signal at the bottom, that sort of cluttery signal is people's movements which don't have a rhythm associated with them. To answer your question earlier about heart rate, this is a particularly interesting area here. You can see that there's no low movement signal course. There's nothing at that 0 level, but just below, well, at just about 0.4 hertz, yeah, so whatever that is in per second, 2 and a bit times a second, 3 a bit times a second, we've got a very, very strong signal. And what we're seeing here, we believe, is with a Parkinson's patient in a bradykinesia state, so really not moving, but the arm is close enough to the chest or attached to the chest, and so we're still seeing the respiratory rate. And what you'll see, and I'll talk a little bit about machine learning models, this is the sort of very, very rich data that's interesting to look at, and you can do it on a patient-by-patient basis, but we really do need advanced computing techniques to be able to get into the richness of data that we see in accelerometry. Incidentally, just so that you get an idea about some of the different things that are going on here, over this side, we're back into a waking period, and much greater signals of strength. So you can see the signal strengths there are much greater because they're up and moving around the place. And these frequency multiples of someone walking. So these sorts of signals will be telling us about a stepping rate, and then we see the multiples of that, the way that the signal processing works. So that takes you to sleep stage, and now this is a really difficult thing. So there's some interesting papers out there, and you can see that there are people thinking about how to do this using these machine learning techniques. There's a reference there using a 3-level classification technique where they believe they're getting some reasonable sensitivities between a REM and non-REM, and then probably a stronger reference, that one, the first one there is a preprint, a stronger reference then on the bottom where basically they've gone through the same work, they've applied the best machine learning techniques that they can, and that you can see the sort they're struggling to discriminate between. They're struggling to tell the difference between REM and non-REM. Interesting, they've got a very complex model they're using there, and it may well be that by simplifying their model, they can get a little bit more sensitivity in other areas. But you'll see more and more of this kind of work going in this area, but also including other sensors as well. And you will have seen in the literature things about including heart rate and other information sources. And I think that's where the most progress is going to be made. But I would anticipate that we'll see some good technology advances in this area over the next few years. Lastly, just in some circadian rhythms. So how do we use those data sources where we've got an epidemiological background? We're not normally collected any data in the lab. We've not got any patient diaries or any of that sort of information. How do we use better algorithms to determine simple sleep parameters, bedtime, rise time, sleep onset, sleep end? So some papers around there. And then, so that's without any other data. And then that other one there is about looking at rest activity rhythms. And accelerometry data compared to actigraphy data gives some exquisite rhythms and pattern understanding within the day and within the night. And so this is an area which is growing quite strongly. Nicely, this paper has also combined that with an experience sampling method. So one of our devices is a wireless-based device which uses the data, retrieves data in real time through an app. And being able to use that same app base to be able to ask people questions during the day, to be able to do the questionnaires in real time over long periods in the field, is something that we'll see changing and being used increasingly. And it's something that we do increasingly in clinical trials now. And we expect to see that going out into clinical practice more. So I'm just going to talk a little bit about how we go about developing that sensor data into health measures that we can use in the real world. So I've talked a little bit about how we can go about this. We've got motion and performance data that we can quantify. We can talk about intensity of movement, these micro patterns and posture. So I've talked about how you can start to bring all of that together. The next thing that we do in our analysis approach is that we define that on an event basis. So we use data-driven approaches. So rather than a fixed epoch, we allow the data to identify a continuous or homogeneous period of data, which we then apply classification and characterization to. And I talked about some of the specific activities of daily living or specific behaviors of interest. And so there's all sorts of things that we've done over the years, detecting toothbrushing, for example. You put it on someone's dominant hand, you can detect toothbrushing quite well if you really focus in on that. So there are different layers at which you can write algorithms with this data. So you can do the general broad spread, where you're really creating some sort of an idea of what the fabric of someone's day looks like that you can then pin specific behaviors to. You can then build those up into a 24-hour cycle, which is probably the big focus here. And then the last level of the digital measures then is how we use then over multiple days to give deeper insight, and across different population groups as well. So you have measures at all those 4 different levels. The framework that we use is what's called a V3, and the reference is here, and this is reasonably new. And this breaks down your verification and validation into these 3 stages. The first one is about making sure that your software, your algorithms are doing what you think they are doing. It's an engineer's job. Life cycle management of software. Is this consistently and correctly applying the right bit of maths to the right data and giving us the right result? The next stage of that is an analytical validation, where we then move to say, well, is this representative of the behavior that I'm actually trying to measure, or the criterion measure? And there are all sorts of different criterion measures we can think about in this space. Often, accelerometry is easier to compare to video-based because you're looking at movement, and they're quite similar, and that works quite well. And increasingly we see video-based analysed or video-scored data as being the criterion measure. And then we move to the last stage around clinical validation, where we're going to say, well, fine, I've got a measure that I know I can create reliably. I know that it's meaningfully measuring what I'm interested in. How does that then help me predict a health outcome, which is the clinical stage, which is where typically we will hand over to many of our customers. So we do the verification work. We work closely with our customers around the analytic validation, and then the clinical's done by our customers. So in terms of that validation, with our devices now, there are over 100 peer-reviewed publications in SLIP, and the majority of them are at that clinical level. There's a link in there, and they're all available on our website. But I literally just last night went off and just picked off the first 5 that are the most recent ones, which is a brilliant diversity of different topics that people are beginning to investigate, and also investigate in many different population areas. So that full list is all available. So I mentioned at the beginning the Digital Clinical Measures Playbook. So this is an initiative that's being run by the Digital Medicine Society. And so last year we put together a pack with many, many great people within the industry, which is publicly available. So that link there, the playbook, go and search for it. There are over 400 slides that bring experience from all around the industry about how we can bring data from remote monitoring and continuous data sources, how we can use that data within health interventions. And they focus on clinical research, clinical care, and public health. The focus at the moment, the biggest area is around clinical research, because that's where the biggest levels of sponsorship and interest are. And certainly our interest is about how we take those learnings into public health. There are all sorts of really interesting recommendations there about deploying these devices that we use and that we've contributed to. So it's a really great resource if you're interested in this area. You'll notice that I've talked in this talk very clearly. I tried to talk about measures. I haven't talked about endpoints. I haven't talked about biomarkers. We use the FDA definition there of a biomarker as a normal biological process, pathogenic process, or a response to an exposure or an intervention. And we try to be quite precise about that. So they become biomarkers when they're used in a particular context of use with a particular purpose. Up until that point, we make sure we're talking about measures. So that's what I can do. And importantly, in the FDA space, a biomarker is not a measure of how the individual feels, functions, or survives, because that's then a clinical outcome measure. So when you're used to working within the clinical space, you need to be quite disciplined about how you use those words. And then obviously, if you've got a biomarker which is appropriate, then if you're going to include that within a clinical trial, at that point it becomes an endpoint. So on the right-hand side, there's just a list of the FDA standard classifications of biomarkers there. Typically, we're looking at predictive and prognostic biomarkers at the moment. And although sometimes when we're measuring lifestyle, we can actually think about that in terms of device safety as well. So in a clinical trial, can I make sure that I've got no unintended effects? So there's some good references there if you're interested in this area as well. Just a last flag that the FDA put forward draft guidance at the beginning of this year around digital health technologies for remote data acquisition. So this is again something that we've worked with, contributed to and have responded to. I think there's still a couple of days left to respond to it. But if you're working in this area and you're interested in collecting measures in the field with digital technologies, this is a great bit of guidance out there. It's probably the first strong guidance that we've had from any of the regulatory authorities. It's just one to be aware of. And then lastly, I just put a slide up just to pick up sort of some of the measures that would come out from our devices, both from an actigraphy sense we talked at the beginning, and then about those more advanced ones, which sometimes are more research-based. Some of those are earlier within that verification validation cycle. I put it up as a list for discussion. I mean, I'm kind of interested about from the group here, what's most useful, what's most credible. Some of these, you could look at, most people would be quite rightly say, well, look, sleep stage it's just not credible at this stage, and I'd fully accept that. It doesn't stop us wanting to do research in there and seeing how we can move it forward, but I certainly wouldn't put our technologies and our algorithms right now forward to say, oh, we can do sleep staging, although you will see other people doing that. So this is my last slide, and it's just a little bit of a summary of this talk and the things I've talked through in terms of measures. Any feedback on this? Any thoughts about this, or any other questions or points for the audience? Hiya.
Sorry, from down here.
No, it's great.
I came in a bit late because of the lunch program.
Oh, I'm sorry about that. We've learned something today.
I'm just wondering, when you say you put out these measures, is this when one takes raw data out of the devices and then uses your software to compute those, or at what stage do these measures come out?
Yeah, so I'd widen it and say, so we're producing, so one of the things, the points I made at the beginning of the talk is that we focus on creating open data, open format data, sensor level data. We support algorithm developers a lot, and we have most of our software is available for research purposes, license free. And we support analysis packages on CRAN and in various open data analysis spaces. So yes, is the answer to your question, but not ours in a proprietary sense. I'm trying to talk generally about where actigraphy is moving towards accelerometry, what potential accelerometry holds, and that with the appropriate algorithms, some of which probably don't quite exist yet, these are the sorts of measures that I think that we're heading to from that data. Sorry, we had a question.
Yeah, my question is, can you differentiate the daytime napping with the nighttime sleep duration?
So the way to think about this, and I always encourage to think about that the devices are very good at knowing what's happening at any instant in time. And at a device level or an event level, the first job that we try to do is isolate a period of data which is homogeneous, that we can analyze, we can classify, and we can characterize. And there are good models that we can apply to say, look, this is a very high probability that this is a sleep event. What happens, and I showed you that architecture, when we start to think about those events in the context with the day, it's at that point that we can then start to make some assertions about whether this is a daytime napping or nighttime. At the early stages, the algorithm is exactly the same, because all it knows is a period of data with a movement profile that looks like this, with this sort of duration. Then if you're going to use an automated bed rise time estimation. Then sleep events that fall out of that, then you might go and examine again and look at the event that happened before them and the event that happened after them. One of the great things about accelerometry, I talked about actigraphy previously, all those algorithms only look backwards. The great thing about being able to do retrospective analysis with accelerometry when you're offline doing the analysis is that you can look into the future as well. And that improves your performance as well. And so that's one of the key things about determining whether a sleep event is likely to be a daytime nap or part of the sleep block or the main rest interval, is to be able to go and look forward and go, well, just a sec, there's a period of activity which looks like a profile of a going to bed activity. I now know that this sleep event was before it, so I've gotten better certainty, better accuracy about its classification.
Hi, thank you. So the most sold wearables nowadays are by far true wireless earbuds. Do you have any strategy on going into analyzing the accelerometers from head-mounted devices?
So I've talked to someone about that today. I talked with reference to the work that I am doing. So I'm not doing that at the moment, but we are doing work. We're involved in a very large study about how we compare with implanted cardiac devices. So not in this area, but all implanted, or most that I know of, implanted cardiac devices, pacemakers, have an accelerometer in them. But they are not well characterized and validated. And what we're doing in that area, we're using our wrist-worn accelerometry as the criterion measure of the gold standard so that we can calibrate the different signals from those different heart-based devices. And I believe that the techniques we use there will be directly transferable in terms of their methodology to head-mounted as well. So yeah, it's work to be done.
So my question is, have you got any data regarding other paroxysmal events, for example, epileptic seizures?
Yeah, so we have worked in collaborations on epileptic seizures before. It's a complicated area, and it's a very deep area to work in. And so I know that there's some ongoing work in that area, but not something that I can comment on right now. I think there are a couple of publications on it in the area. And again, it's one of those ones which the data could be very, very useful adjunct to other things. Certainly, I did some early work in nighttime epileptic prediction, and you know that's quite a serious medical device, isn't it? So you've got to be very, there's a lot of work you have to do in that area before you can make any kind of claim. And that's work I know was started about 6 years ago, and I haven't checked in on it recently. Right. Thank you very much for taking the time. It's been a pleasure to talk to you, and it's been a pleasure to hear from the audience as well. Thank you.